Okay, here we go. Kinesiology 230. This is chapter 2. We're still talking structure and function of the cardiorespiratory system. This is presentation number 2, and we're talking oxygen transport and hemoglobin. So hemoglobin is a protein within the blood cells, and it contains iron, and it's the interaction between the oxygen and the iron that causes oxidation and gives it that kind of red look. Now, the hemoglobin itself, the way it's constructed, has the ability to bind with anywhere between 1 and 4 oxygen molecules. So there are 4 different irons within a hemoglobin. And we'll get into this in a second, a little bit deeper here. But what happens is when an O2 molecule binds, meaning an oxygen molecule binds with one of the irons in a hemoglobin, that hemoglobin itself becomes more readily accessible to having more iron and oxygen interact. And this term is called cooperative binding. And this binding itself is what allows the tipping point to have more oxygen ride on board with or on a hemoglobin. So the hemoglobin is what's called a tetramer. Tetra for 4, and then mer is parts. So it's literally made up of 4 main parts. And you have 4 main little hemigroups, and each hemigroup, like I mentioned before, has one iron that can interact and connect with the oxygen molecule. And the picture, that's kind of a rough drawing that you can pick up anywhere on the internet, is this. Now, when I was in undergrad, it was very much written like, here's the platelet, and here's 4 little matchsticks on top, and on top of the matchsticks are where the Fe, the iron, is or are, and that's what would interact. Now, it's a little bit different now in terms of, I'm sure, since I went to college, you have these different renderings of what hemoglobin looks like through the ability to have greater microscopic evaluation of blood cells. I digress. So you can see within here, you have these 4 different colors, and the 4 different colors, each one has an iron, tucked in here, here's one, and here's one. And those allow, like I said, the ability to interact with the oxygen. Now, when I was in college years ago, and this was way before my time. The 4 Tops were a Motown group years before I was even born. But when I visualized this, I visualized the 4 Tops were driving in their Hemi, right, their car, to their performance. And when an oxygen molecule would hop on board with them to go to the show, this caused the car to turn red. And so what happens is, once that first oxygen molecule hops on board with them to go to their show, then it's really easy for them to pick up the next 3 oxygen molecules to go with them to their show. Kind of viewed them as like iron groupies, if you will, or the 4 Tops groupies. Anyways, so the way I would just wrap myself around this is when the 4 Tops were driving in their Hemi, they would pick up oxygen molecules along the way, and that would give the car its red color. And it worked for me. So each Hemi group has 1 iron and can interact with 1 oxygen molecule. We got that. When the first one binds with the iron, it creates a greater availability, or ability, I should say, for subsequent oxygen to bind with the next iron. So once you have 1, you can get the next one, the next one, and the next one. There's a couple different factors that play into this. They get kind of complex, but we'll leave it at that for right now. And when you look at this is in the book. And this is referred to as the oxyhemoglobin dissociation curve. You have a couple things that need to be parsed out here. You have P of O2, meaning this is partial pressure of oxygen. And you have partial pressure of oxygen, you have partial pressure of CO2. And there's a constant ebb and flow between the partial pressure of oxygen and the partial pressure of CO2. Based on what I said in the earlier conversation regarding red line, blue line, one can pretty quickly put together where the partial pressure of oxygen is the highest, probably in the red line, and where the partial pressure of oxygen is the lowest, probably in the blue line. And then conversely, where the partial pressure of CO2 is probably the highest, probably the end of the blue line. And then the partial pressure of CO2 is probably the highest would be the end of the blue line. The partial pressure of CO2 being the lowest would be the beginning of the red line, if I can say it correctly. And we'll see this here in a second. I'll reiterate that just to make sure nobody's confused. As you look at this curve, this gives us a sigmoid plot, and it gives us a nice S curve. And you look at the number 1 and the number 2. The number 1 represents up here the loading portion of the curve. Saturation stays high even when with large changes in partial pressure of oxygen, and oxygen is delivered to the tissues when you have this higher oxygen content. When you have a lower oxygen content itself, it ends up not having the ability to exchange, if you will. The partial pressure is just not there because gases work in pressure gradients. Gases work from high pressure environment to low pressure environment, never the opposite way. So if you have low partial pressure of oxygen, it makes sense that you're not going to offload oxygen. So unloading, when you look at number 2 here, during this part of it, as you have this saturation rate goes up and up and up and up and up, you get to the 100% up top. And I want to point this out on the next slide in terms of when they evaluate, often they evaluate and they talk about this curve, but they don't really explain like where the oxygen level is the highest and where the oxygen level is the lowest. And I think it serves purpose to be able to have that conversation. But also you have to look at this in terms of what happens in the body when we start to work out. So if we go ahead and go to the next slide here, we think of this red line, blue line example. And as I mentioned before, you have the partial pressure of oxygen. Well, the partial pressure of oxygen is going to be at its highest when, because you have the most oxygen in the lung, most oxygen in the blood when it comes out of the lungs and then goes off to service the body. So you're going to have not only the highest blood pressure, but you're going to have the highest oxygen saturation rate. As you work through the system and you get to the blue line and deoxygenated blood is returned to the heart, you're going to have a lower partial pressure of oxygen. What happens is the exact opposite with CO2. When we leave the heart, the ventricle on the left side, this will be the lowest point of partial pressure of CO2. As we go through and we're offloading oxygen and onloading CO2, we have more and more and more CO2. When we get to the right atrium, you're going to have the highest partial pressure of CO2. So notice how as we switch from red line to blue line, the pressure gets more. You can just imagine like your train car is just full of people shoulder to shoulder, all wearing red shirts, red jackets, red suits, etc. And they're all crammed in there shoulder to shoulder. And as they move through and they go to the muscles and they jump off and they service the muscles, blues are jumping on. And you have this kind of pressure gradient that's happening as we're switching from red line to blue line. You go from less and less and less oxygen, which is reducing the amount of partial pressure in the oxygen side, and you're increasing the partial pressure on the blue side. So it returns to the heart, and it then goes off from here on the right atrium to the right ventricle, up on over to the lungs, and it actually separates to both sides. It's not like it goes into the right lobe of the lung and then it goes off into the left lobe of the lung. And it offloads here and it onloads there. It actually happens at an alveolar level. There's a gas exchange that happens across both lungs, and then it goes back into the heart. So you're really looking at this kind of ebb and flow of partial pressure that happens. And as we go back to our hemoglobin here, we look at this. This is one of the charts from the book, and I've kind of adapted it to our conversation here. When you look at the y-axis, it represents the percent of saturation, the hemoglobin oxygen saturation, right? So if you're at 0% versus 100%, this curve has that sigmoid plot that curves, right? And we go ahead and look at this, and we can start to really interpret what's going on. We have a normal pH of 7.4. When the pH level drops, we know we become more acidic. There's acidosis. When the pH level increases, it's alkalosis. And depending how acidic or alkalytic we are, will depend how much the curve actually moves and how much it shifts. And what I really want to get across is when you look at this, when you have a high acidic environment, you have a pH of 7, notice the move to the right, but notice what it also does over here. So you have this hemoglobin oxygen saturation rate that should be at 100%, but it's actually just a little bit below that. So as the blood becomes more acidic, it just can't fully accept the oxygen molecules into the hemoglobin. And we can take this a step further and we look at, okay, where you have the highest exchange of oxygen and the highest partial pressure of oxygen versus the lowest partial pressure of oxygen. We know the highest partial pressure of oxygen is in the lungs. And we look at this and go, okay, the partial pressure, and this is not in percent down here. Notice it's millimeters per mercury in terms of pressure. This ends up being 120 millimeters per Hg. Whereas when you start to work out and you see that you have this lower and lower oxygen saturation, it starts to dip down into the partial pressure being 30. So notice the ebb and flow that happens where when you have greater saturation, it moves up and to the right, you have greater pressure. When you have maximal saturation, you have the highest pressure. Converse down here, we do the exact opposite. So with this, you'll see this in a quiz question in the book, I know, or a test question, I know 100%. We operate at 7.4 on a pH level. Higher pH levels are 7.45, which is alkalosis, and then lower pH is, say, like roughly 7.35. This is right from the book, which is acidosis. With the lower pH levels, right, so we become more acidic, the curve shifts to the right. With increased body temperature, this will cause a shift to the right, meaning there's a reduced affinity, like we just saw in our last slide, that there's a reduced affinity for the oxygen to bind with or interact with the iron in the hemoglobin. So it can't carry as much oxygen to service the muscles. So realize when body temperature goes up, the level of acidity goes up, and also the other part of it is you have more CO2 that you have to blow off. So oftentimes when we work with our athletes and we have them do intense training, we guide them to do some type of active recuperation, walking around, just kind of move around a little bit so they can actually have an increase of an active recuperation. They can have an increase of active recuperation to basically blow off more CO2, but also pull in a little bit of oxygen. But the big part is blowing off CO2, so we buffer that acidity in the blood itself. And we can shift that curve back to the left and be able to have greater oxygen saturation. All right, I'm going to break off from here and move on to the next one.